Here is something that should not be possible. Physicists can predict the behavior of a single particle so precisely that their numbers match experiments to more than 10 decimal places, the most accurate predictions in the entire history of science. And yet, when you ask that same theory one simple question, where exactly will this one particle land? It flatly refuses to answer. It will only give you the odds. Not because our instruments are too crude, not because we are missing some hidden piece of information, but because, according to our deepest theory of reality, the particle itself does not carry a single definite answer until the instant something interacts with it. This is not a mistake hiding inside the equations. This is the equations working exactly as intended. And tonight, we are going to uncover why the universe, at its foundation, seems to deal only in possibilities. If you enjoy slowing down and really thinking through the strange machinery underneath reality, a quick like or subscribe genuinely helps this channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. There is a fact about modern science that almost nobody outside of physics ever stops to find strange, and once you do stop to look at it, it becomes one of the most unsettling facts you can encounter. Take the theory that governs the smallest pieces of the world, the framework physicists reach for when they want to describe an electron, or a beam of light, or the magnetic behavior of a single particle. That framework can produce predictions of a precision that has no equal anywhere else in human knowledge. There is a particular quantity describing how an electron responds to a magnetic field, and the theoretical prediction for it agrees with the measured value to something like 12 digits of accuracy. To picture what that means, imagine measuring the distance from one coast of a continent to the other and being correct down to the width of a single human hair. That is the level of agreement we are talking about. This is not a theory that fumbles. This is the most successful description of nature ever written down. And yet, ask that same theory the most basic, childlike question you can imagine. You have a single particle. You are about to detect it. Where will it be? And the theory, this triumphant, hyper-accurate, unbeaten theory, will not tell you. It will not give you a location. What it will hand you instead is a list of possibilities, each one stamped with a number, a probability, the odds that this is where the particle turns up when you finally look. Run the experiment once and you get one answer. Run it again under conditions as identical as you can possibly make them. Same setup, same preparation, nothing changed that you could ever detect. And you may very well get a different answer. The theory predicted both. It predicted the spread. What it refused to predict was which single result this particular run would give you. Now, the natural reaction, the reaction nearly everyone has the first time they meet this, is to assume it is our fault. We must be missing something. The particle surely does have a definite location, and we simply do not know it yet. Our equipment is too coarse. Our knowledge is incomplete. There is some hidden detail we have failed to track, and if we were only clever enough or careful enough, we would close that gap and recover a clean, definite answer. That assumption feels not just reasonable, but obviously correct. It is how the entire rest of our experience works. When a weather forecaster says there is a 70% chance of rain tomorrow, nobody believes the sky is fundamentally undecided. The atmosphere is going to do something perfectly definite. The forecaster is just working with incomplete information about an enormously complicated system. The probability lives in the forecaster's head, not in the clouds. The deep and genuinely disorienting claim at the center of quantum physics is that this everyday intuition does not carry over. The probabilities are not a confession of ignorance that better tools would erase. According to the theory, and according to a long chain of experiments designed specifically to test exactly this question, There are situations where the particle does not possess a single definite answer waiting to be uncovered. The indefiniteness is not in our knowledge, it is in the situation itself. And tonight, slowly and carefully, we are going to take that claim apart and understand what it could possibly mean for reality to be built that way. But to do that honestly, we have to start by correcting something, because there is a phrase that gets attached to this subject so often that it has practically fused to it, and it is misleading in a way that quietly sabotages everything that follows. The phrase is that quantum physics is the physics of very small things. You hear it everywhere. It sounds harmless. It even sounds helpful, because it is true that the strangeness shows up most vividly when you are dealing with single particles and tiny systems. But describing quantum physics as merely the physics of the small is like describing law as the study of courtrooms. Yes, courtrooms are where you see it most dramatically, but the law is not a fact about rooms. It is a system of rules that applies whether or not anyone is standing in a courtroom. Quantum physics is the same. It is not fundamentally a statement about size. It is a framework. So let us be precise about what that word is doing, because it is the foundation everything else rests on. When physicists call quantum mechanics a framework, they do not mean a single equation or a single discovery or a list of weird effects. They mean something closer to a rule book, a structured procedure for doing three connected things. First, the framework tells you how to take any physical system you care about and write down a description of it, a description of a very specific mathematical kind. Second, it tells you how that description changes over time when the system is left alone, how it evolves, smoothly and predictably according to a fixed rule. And third, it tells you how to connect that description to the things you can actually observe, how to go from the abstract description to the concrete numbers a real detector will spit out. That is the framework. A way to describe, a way to evolve, and a way to predict what you will see. What makes it a framework rather than a single theory is that it does not, by itself, tell you what specific system you are dealing with. It is a template. You can pour an electron into it, or a photon, or a whole atom, or a vibrating crystal, or a current flowing through a loop of superconducting wire, and the same machinery applies. The rules for describing, evolving, and predicting stay the same. Only the details you feed in change. This is exactly why the very small things definition undersells it so badly. The framework is not about the size of the thing. It is about the structure of how nature is described at the most fundamental level we have reached. The smallness is incidental. It is just that for large, everyday objects, the quantum strangeness gets buried so thoroughly that you would never notice it, for reasons we will get to much later. But the framework is still running underneath. It does not switch off when objects get big. It just hides. Now, here is where we meet the single most important idea in this entire subject, the object that sits at the dead center of the framework, and that everything we discuss tonight will circle back to. The thing the framework asks you to write down, the description it works with, has a name. It is called the quantum state. And almost every confusion people have about quantum physics, including the confusion about probability we opened with, comes down to a misunderstanding of what the quantum state actually is. So let me build it up carefully, because this matters more than anything else I will say. Think first about how you would describe a system in ordinary pre-quantum physics. Suppose I hand you a single billiard ball rolling across a table, and I ask you to describe its state completely, to write down everything there is to know about its motion at this instant. You would tell me where it is, its position, and you would tell me how fast it is going and in what direction. It's momentum. Give me those, position and momentum, and in the old picture you have told me everything. The state of that ball is a complete set of definite values. It has a location, full stop. It has a velocity, full stop. Every property you could ask about has a single answer sitting there, whether or not anyone is looking. The description is just a faithful inventory of facts that already exist out in the world. The ball has those properties. You are merely reading them off. That is the intuition we all carry, and it is the intuition the quantum state breaks. Because the quantum state is not an inventory of properties the system already definitely possesses. It is something stranger and, once you absorb it, something far more powerful. The quantum state is a complete catalogue of every possible result you could get from the system, together with exactly how the theory weights each of those possibilities. It does not say, the particle is here. It says, in effect, if you go looking for the particle, here are all the places you might find it, and here is the precise mathematical weighting that determines how the odds break down across those places. I want to slow this down, because the leap is subtle, and it is easy to slide right past it. In the billiard ball picture, the description points at a fact. There is a location, and the description names it. In the quantum picture, the state does not point at a single hidden fact about location. The state is the thing that contains all the candidate facts at once and tells you how they are balanced against each other. The definite answer, the single location, is not sitting inside the state waiting to be read off. It is not there yet. What is there is the full structured set of what could be, and the relative weight of each option. If that sounds like a fancy way of saying, we just do not know which one it is, then I have not yet made the distinction sharp enough, and I'm going to spend a good portion of this narration making it sharper, because that exact slippage is the misunderstanding I most want to dismantle. For now, plant a flag on this one sentence and hold on to it. The quantum state is not a description of what is, with some parts left blank because we are ignorant. It is a description of what could be and how the possibilities are weighted. And that fuller object is the most complete description the framework allows. There is, according to the theory, nothing more complete hiding behind it. The catalogue of possibilities is not a stand-in for the real answer. As far as the framework is concerned, the catalogue is the most real and most complete thing there is to say. Let me make this concrete with a single particle, because abstraction is the enemy of understanding here. Picture an electron that has been prepared in some careful way and is now sitting, isolated, inside a piece of equipment. In the old way of thinking, that electron is somewhere. It has a position. We might not know the position, but the electron does, in the sense that there is a definite fact of the matter, a specific point in space where the electron genuinely is, right now, independent of whether we ever check. The quantum state of that electron does not work like that. The state assigns to every point in the available space a quantity, and that quantity, once you process it through the rules of the framework, tells you how likely the electron is to be found at that point if you perform a measurement of its position. Not where it is, but where it would be found. Those are not the same statement, and the entire mystery lives in the gap between them. So when the theory says the electron's position is described by this spread out state, covering a whole region rather than sitting at one point, the honest reading is not the electron is hiding somewhere in that region and the state shows our ignorance about which point. The honest reading, the one the framework actually commits to, is that the electron's position is genuinely not a single definite value at this moment. The state, spread across the region, is the complete truth about the electron's position. The single value only comes into existence when a measurement forces the issue. And which value you get when it does come into existence is governed by the weighting the state encoded all along. Now you can see, even this early, where the probabilities are coming from, at least in outline. If the most complete description of a system is a catalogue of possible outcomes with weights attached, and if the system genuinely does not carry one definite answer until an interaction extracts one, then of course the theory can only tell you the odds. The probabilities are not a patch over our ignorance. They are a direct readout of the structure of the state itself. The state contains the possibilities and their weights. The act of measurement selects one possibility, and the weights tell you how the selection tends to fall when you repeat the whole thing many times. The probability is not in the physicist's head the way the weather forecaster's 70% lives in the forecaster's head. The probability is in the state, and the state, according to the framework, is in the world. I can already feel the resistance this provokes, because I felt it myself, and it is the right instinct to push back. The objection goes like this. Fine, you say the electron has no definite position until measured. But how could you possibly know that? Maybe it does have a definite position, you just cannot see it, and your beautiful, complete description is actually an incomplete one, and there is a deeper layer underneath, full of the definite values you are insisting are not there. This is not a foolish objection. It is, in fact, one of the most serious objections ever raised against quantum physics, and some of the greatest minds in the history of science raised it and fought hard for it. The idea that there must be hidden details underneath, some hidden inventory of definite values that the quantum state is merely summarizing, is so natural that resisting it feels almost perverse. I am going to be completely honest with you about the structure of what follows, because I think you deserve it. We are not going to settle that objection by waving our hands and insisting the textbook is right. We are going to earn the answer. There is actual physical evidence, real experiments built specifically to distinguish between the particle has a hidden definite answer and the particle genuinely has no single answer until measured. And those experiments come down again and again with extraordinary consistency on a particular side. But that evidence requires building up some machinery first, and so for now, I am going to ask you to hold the question open, rather than letting your intuition slam it shut. Notice the intuition. Notice how strongly it insists that the definite values must be there somewhere. And then set it gently to the side, because by the time we are done, you will see precisely why nature appears to disagree with it. Let me return to the framework and add a piece I gestured at, but have not yet placed. Because the quantum state is not a frozen thing. Remember that the framework does 3 jobs: describe, evolve, predict. We have spent our time on the first, on what the state is, but the second job, the evolution, is quietly one of the most surprising and least appreciated facts in the whole subject, and it sharpens the puzzle rather than softening it. Here is the surprise. When a quantum system is left alone, when nothing is measuring it and nothing is disturbing it, its state changes over time in a way that is completely smooth, completely predictable, and absolutely deterministic. There is a rule, a fixed equation, that takes the state you have now and tells you, with perfect certainty and no probability whatsoever, exactly what the state will be a moment from now, and a moment after that, on into the future. Let that sink in, because it cuts directly against the cliché that quantum physics is random or fuzzy through and through. The evolution of the state is not random at all. It is as rigid and clockwork as anything in the old physics. If you know the state now, you know the state later. Exactly. So where on earth does the randomness come from? This is the crux, and it is worth stating as plainly as I can. The state evolves deterministically. The catalogue of possibilities, with all its weights, marches forward in time according to an exact and predictable rule. The probability, the genuine unpredictability, does not enter during this smooth evolution. It enters only at the moment of measurement, the moment of the third job, when you reach in and ask the system to deliver a single, concrete answer. At that moment, and only at that moment, the deterministic catalogue of possibilities gives way to one outcome, selected with odds set by the weights. So quantum physics is, strangely, both perfectly deterministic and irreducibly probabilistic, and the line between the two falls exactly at the act of measurement. The state evolves with certainty. The outcome is drawn with chance. This already tells you that measurement is going to be a loaded and important word, far more loaded than it sounds, and we are going to have to be extremely careful with it later, because it is the source of more confusion and more bad popular mythology than any other concept in the field. People hear that measurement is special and immediately leap to the idea that there is something magical about human observation, that a conscious mind is reaching in and conjuring reality into being by the act of looking. I want to head that off now, even though we will not fully resolve it until much later. That mystical reading is not what the framework says, and it is not what the evidence supports. Measurement, as we will see, is a physical interaction, the kind of thing that happens constantly throughout the universe, whether or not any living creature is anywhere nearby. The challenge is to understand why that particular kind of interaction has the special role it does, and we will get there. For now, just register that measurement is the hinge on which the determinism turns into probability, and file away a healthy suspicion of anyone who tells you it requires a mind. Let me try to gather all of this into a single coherent picture, because we have covered a lot of conceptual ground, and I want the shape of it to be clear before we go deeper. Quantum physics is a framework, a rulebook. The rulebook centers on an object called the quantum state, which is not an inventory of properties the system definitely has, but a complete catalogue of the outcomes the system could produce, each weighted by the rules of the theory. Left alone, that state evolves through time with perfect deterministic smoothness. But when the system is measured, when it is forced to deliver one concrete result, the catalogue of possibilities collapses to a single outcome, selected with probabilities read directly off the state's weights. And the radical claim, the one our entire intuition rebels against, is that before that measurement, the single definite answer was not merely unknown to us. It did not exist as a single definite answer at all. The fullest, most complete, most truthful description of the system was the catalogue of possibilities itself. If that claim is correct, it forces a genuinely new picture of what it even means for something to be real. In the world of the billiard ball, reality is a vast collection of definite facts. Every object has every property pinned down to a specific value at every instant, and physics is just the project of discovering and tracking those values. The quantum state suggests that this picture, however natural, is not how the world is built at its foundation. At the foundation, the most complete thing you can say about a system is often not a set of definite values, but a structured field of possibilities. Definiteness, the crisp, single answer we take for granted, is not the starting material of reality. It is something that emerges, something produced when the right kind of interaction occurs. Reality, at bottom, traffics in the possible, and the actual is something that crystallizes out of it. I realize how strange that sounds, and I want to be careful not to oversell it or dress it up in more mystery than it deserves, because the genuine article is strange enough without embellishment. So let me be disciplined about exactly what has and has not been established so far. What I have given you is the structure of the framework and the role of the state within it. I have told you that the framework describes systems with these catalogues of possibility, that the catalogues evolve deterministically, and that measurement draws single outcomes with probabilities set by the catalogue's weights. That structure is not in dispute. It is the working machinery that physicists use every single day, the machinery behind that 12-digit precision we opened with. The technology in the device you are using to hear these words depends on this framework being right about how the world works at small scales. It is tested constantly, and it does not fail. What I have not yet done, and what I owe you, is the harder part. I have asserted that the indefiniteness is real, that the missing definite answer is genuinely missing and not merely hidden, and I have asked you to hold your skepticism in reserve rather than letting it close the question. I have introduced the idea that the state contains several possibilities layered together, but I have not yet shown you what that layering actually looks like, or why we should believe the layers are physically real rather than a convenient fiction. I have used the word measurement as though it were obvious, when in fact it conceals one of the deepest open problems in the subject. And I have drawn a sharp line between not knowing an answer and there being no answer to know. But I have not yet given you the tools to see why that line is not just philosophical wordplay, but something with hard, testable, experimental consequences. Each of those debts is going to be paid. The layering of possibilities, the thing inside the state that makes it more than a list, has a name and a structure, and understanding it is the key that unlocks why interference happens, why the possibilities are not just ignorance, and why a hidden inventory of definite values cannot quietly be smuggled back in. The distinction between ignorance and genuine indefiniteness has a precise expression in the relationship between certain pairs of properties, a relationship so fundamental that it is woven directly into the mathematics rather than tacked on as an afterthought. And the role of measurement, the hinge where smooth determinism turns into probabilistic outcome, can be understood as a physical process without any appeal to minds or magic, once we see what happens when a small quantum system makes contact with the vast, warm, complicated world around it. But notice what we have already accomplished, because it is more than it might feel like. We started with a paradox that sounded like a flaw, a theory of unmatched precision that nonetheless refuses to predict single outcomes and offers only probabilities. The instinctive reading of that paradox is that the probabilities mark a failure, a gap in our knowledge, a sign that the theory is incomplete and that a better theory would restore the definite answers we expect. What I have been laying out is a completely different reading. The probabilities are not a failure. They are a faithful report of the structure of the quantum state, and the quantum state, with its catalogue of weighted possibilities, is not an incomplete description crying out to be finished. It is, according to the framework and according to a great deal of experiment, the complete description. The probabilities are there not because the theory is too weak to do better, but because the world, at its foundation, is the kind of place where a single, definite answer simply does not exist until something draws one out. That is the inversion at the heart of everything that follows. We tend to assume that uncertainty is a measure of our distance from the truth, that the more uncertain we are, the further we stand from the real, definite facts of the matter. Quantum physics quietly proposes that, at the deepest level, the uncertainty is not the distance to the truth, it is part of the truth. The spread of possibilities is not a veil hiding a definite reality behind it. The spread of possibilities is the reality, until the moment an interaction forces it to commit. And so the question that pulls us forward, the question we have to answer to make any of this believable, is exactly the one your intuition has been shouting since the beginning. If the particle really has no single definite position, no hidden inventory of values waiting to be uncovered, then what is the difference, in actual practice, between that radical claim and the boring, sensible claim that the particle does have a definite position and we simply have not measured it yet? If both pictures predict the same probabilities, how could anyone ever tell them apart? It would seem like a distinction without a difference, a piece of philosophy with no teeth. It is not. The two pictures make different predictions, in certain very carefully arranged situations, and those predictions can be checked. The thing that lets us tell them apart, the physical phenomenon that exposes the difference between a genuine spread of possibilities and a mere veil over hidden definite values, comes from looking closely at what it actually means for several possibilities to be layered together inside a single state, and what happens when those layered possibilities are allowed to meet. That layering, and the way the layers can reinforce or cancel one another, is where the abstract talk of possibilities turns into something you can see in a laboratory, something a hidden definite answer could never reproduce. That is where we are headed next. So we are left holding a promise and a problem. The promise is that there exists some real, physical difference between a particle that genuinely has no single definite answer and a particle that secretly does, with the answer merely hidden from us. The problem is that, on the surface, those two stories sound identical. Both predict that when you measure, you get one result. Both predict that if you repeat the experiment many times, the results spread out according to certain odds. If that were the whole story, the difference between them would be untestable, a matter of taste, the sort of thing reasonable people could argue about forever without anyone ever being able to settle it. To find the difference, we have to look much more closely at the thing I have been calling, somewhat vaguely, the catalogue of possibilities. We have to look at what it actually means for several possibilities to live together inside a single quantum state. And the name for that living together, the central structural feature of the quantum state, is superposition. Now, superposition is a word that has been so thoroughly mangled by popular accounts that I almost hesitate to use it, because the version most people carry in their heads is not just simplified, it is actively wrong in a way that blocks understanding. The cartoon version goes like this. A particle in superposition is in two places at once. A cat in a box is alive and dead at the same time. An object is doing two contradictory things simultaneously. You have heard some flavour of this, and it is repeated so often that it has the ring of established fact. I'm going to ask you to set it down, because almost every word of it points in the wrong direction. Here is the trouble with "in two places at once." That phrase smuggles in exactly the assumption we are trying to escape. It pictures the particle as a little object that definitely has a location, and then tries to fix the weirdness by saying it has two locations instead of one. But two definite locations is still a picture built entirely out of definite locations. It is the billiard ball worldview with an extra ball bolted on. That is not what superposition is. Superposition is not the particle being at two places that are each definitely real. It is the state holding several potential outcomes layered together, none of which has yet been actualized into the single concrete fact that a measurement would produce. The particle is not at location 1, and it is not at location 2, and it is not cheerfully at both. The state is a single thing that, when interrogated about position, contains location 1 and location 2 as possibilities, woven together, weighted and waiting. Let me try to give you a cleaner handle on this, because the difference between two definite places and one state holding two possibilities is the whole game, and it is genuinely slippery. Think about the difference between a mixture and a blend. Or better, think about a musical chord. When a piano plays three notes together to make a chord, the result is not three separate notes taking turns, and it is not one note that is secretly three notes hiding behind a curtain. It is a single sound with a particular structure, a sound that genuinely contains all three frequencies layered into one thing. The chord is one object. Its threeness is not three separate objects standing side by side. It is the internal structure of a single object. Pull the chord apart with the right tool and you can recover the individual notes, but as it sounds, It is one unified thing with a layered interior. The quantum state in superposition is something like that. It is one state. Its multiple possibility character is not a collection of separate definite particles. It is the internal structure of a single description. I want to be careful, because every analogy in this subject leaks, and I do not want you to walk away thinking a particle literally is a chord. The point of the chord is narrow and specific. It is meant to break the grip of the idea that several things layered together must mean several separate definite things. A chord shows you that one object can have a genuinely layered interior without being secretly a crowd. That is all I want from it. Hold that and let the rest of the analogy fall away. Now we need to add the piece that turns this from a vague image into actual physics, because so far, layered possibilities is still just words, and words are cheap. Inside the quantum state, each of those layered possibilities does not merely carry a probability. It carries something richer, something that the probability is eventually squeezed out of. Each possibility carries a quantity called an amplitude. And the amplitude is the secret ingredient, the thing that makes the quantum state more than a list of options with odds attached, the thing that ultimately exposes the difference between genuine indefiniteness and hidden ignorance. So I need to spend some real time on what an amplitude is and why it matters, because if you understand amplitude, you understand the deepest structural fact about the quantum state, and almost everything else follows. Start with what a probability is and what it cannot do. A probability is a number between 0 and 1. Something with probability 0 never happens. Something with probability 1 always happens. Something with probability 1/2 happens about half the time. Probabilities are humble, well-behaved numbers, and crucially, they only ever add up. If outcome A can happen one way with some probability, and the same outcome A can also happen by a second, separate route with some other probability, then the total chance of A is just the two probabilities added together. More routes to an outcome can only ever make that outcome more likely or leave it unchanged. Adding possibilities in the ordinary world of probabilities can never make something less likely. You cannot have two ways for an event to happen that, when both are available, somehow combine to make the event happen less often than either route alone. With ordinary probabilities, that is simply impossible. Opportunities accumulate, they do not cancel. Amplitudes do not behave this way, and that single fact is the crack through which all the strangeness pours. An amplitude is the quantity the quantum state actually assigns to each possibility, and it is not a humble number between 0 and 1. It is a richer kind of quantity, one that has, in addition to a size, something like a direction or a phase, a feature that has no counterpart in ordinary probability at all. You can think of each amplitude, very loosely, as a little arrow. It has a length, and it has an orientation, a way it is pointed. The probability of an outcome is recovered from the amplitude by taking its length and squaring it, throwing away the orientation in the process. So when all you care about is a single possibility in isolation, the orientation does not seem to matter, and the amplitude behaves, for that one purpose, like a slightly disguised probability. This is why, in simple situations, the whole amplitude machinery can hide, and you would never know it was there. But the orientation does not actually go away, and the moment you have more than one route to the same outcome, it comes roaring back and changes everything. When a single outcome can be reached through two different possibilities that are both present in the state, you do not add their probabilities. You add their amplitudes first, arrows and all, taking their orientations into account, and only then do you square the result to get the probability. And here is the consequence that has no equal anywhere in ordinary experience. If two amplitudes point in the same direction, adding them makes a longer arrow, and the outcome becomes more likely even than either route would have produced alone. That part feels familiar, like reinforcement. But if the two amplitudes point in opposite directions, they partially or even completely cancel. Two ways for something to happen, both genuinely available, can combine to make that something happen less often, or even never at all. Add a second root to an outcome and watch the outcome become impossible. That is not a thing probabilities can do. That is a thing amplitudes can do. And the universe, it turns out, runs on amplitudes. This phenomenon, where the layered possibilities inside a quantum state combine, sometimes reinforcing and sometimes cancelling, has a name. It is called interference. And interference is the single most important piece of evidence in this entire subject, because it is the thing a hidden definite answer cannot fake. Let me say clearly why. Because this is the payoff I promised. The moment where the abstract distinction between ignorance and genuine indefiniteness grows teeth and becomes something you can actually test. Suppose you took the boring, sensible view we keep being tempted by. The particle really does have a single definite answer all along, you just do not know which one. And the quantum state's spread of possibilities is nothing more than a tally of your ignorance, a list of the options the particle might definitely be, with odds reflecting how often each turns up. On that view, the particle, on any given run, is genuinely taking one route and not the other. It definitely goes one way. You just do not know which. And if the particle definitely takes one route on each run, then the routes are mutually exclusive alternatives, and the rules of ordinary probability must apply. Open up a second route, and the chance of the outcome can only go up or stay flat. It can never go down. A definite particle following a definite path cannot cancel itself out by being offered a second path it did not take. So here is the clean test, the fork in the road that nature is forced to choose between. If the spread of possibilities is mere ignorance over hidden definite answers, then opening additional routes to an outcome can only ever add up. And interference, real cancellation, the outcome becoming less likely when more paths are available, must never appear. But if the spread of possibilities is genuine superposition, with amplitudes carrying their orientations, then opening additional routes can produce cancellation, and we should see outcomes that become impossible precisely because a second path was made available. These are not two phrasings of the same prediction. They are two different predictions about what will actually be measured. Ignorance forbids cancellation. Superposition permits it. And so we can simply go and look at which one nature does. Nature does the cancellation. It does it reliably, repeatedly, in experiment after experiment, across an enormous range of systems. When you arrange a situation so that a quantum system can reach a given outcome by two or more routes, and you do not force it to reveal which route it took, the outcomes distribute themselves in patterns of reinforcement and cancellation. Bright regions where the amplitudes added up, and dark regions where they cancelled out. Regions where the system simply never arrives, even though each route, taken on its own, would have delivered it there plenty of times. The presence of a second possibility makes certain outcomes vanish. That is interference, and it is the fingerprint of genuine superposition. A hidden, definite, ignorance-only answer cannot produce it, because a particle that really took one definite route cannot cancel itself against the route it did not take. The cancellation only makes sense if both possibilities were genuinely present, genuinely contributing their amplitudes, genuinely layered together inside one state, rather than one of them being secretly the real story, and the other a mere unrealized maybe. I have been deliberately abstract about the experimental setup, and I have done that on purpose, because the famous demonstration of this, the one involving particles sent toward a barrier with two openings, has been described so many times that I worry the familiarity dulls the shock. The pattern of bright and dark bands that builds up on the far side, the dark bands landing exactly where each opening alone would have sent plenty of particles, is the visible signature of amplitudes cancelling. But I want you to grasp the logic underneath any particular apparatus, because the logic is what matters, and the logic is general. Whenever a quantum system has more than one way to reach an outcome, and nothing in the world records which way it went, the amplitudes for the different ways combine with their orientations before any probability is computed, and the result can be cancellation. The specific machinery is just a stage. Interference is the play. And now watch what happens, because this is the truly remarkable part, the part that pins the whole thing down. Suppose you take that same setup, the one producing beautiful interference, and you add a detector that records which route the system actually took on each run. You do nothing else. You simply gain the which way information. The interference pattern disappears. The cancellation evaporates. The dark bands fill in, and the outcomes redistribute themselves exactly as ordinary, boring probability says they should, as if each system had taken one definite route all along. Remove the which way detector, and the interference comes back. This is not a story about clumsy equipment knocking the particle around, although that misreading is common and tempting. It is something far more pointed. The moment the world contains a definite record of which possibility was realized, the possibilities stop being layered together, and you recover the ordinary, no cancellation behavior. The interference exists precisely when, and only when, the alternatives remain genuinely superposed, with no fact anywhere about which one happened. The instant a fact about which way comes into being, the superposition is gone, and the cancellation with it. Sit with that, because it is doing enormous work. It tells you that superposition is not a permanent, fixed property of the particle. It is a property of the situation, specifically of whether the alternatives are kept layered together or are separated out into definite, recorded options. When the alternatives are layered, amplitudes combine and you get interference. When the alternatives are separated, when the world has registered which one occurred, you get plain probability. And this gives us the sharpest possible answer to the objection that dogged us from the beginning. The objection that maybe the particle has a hidden, definite answer all along. If it did, the interference could never appear, because a definite answer means a definite route, and a definite route forbids cancellation. The interference appears. Therefore, in those situations, there was no single definite route. The layered possibilities were genuinely both present and genuinely contributing. The indefiniteness is real. Let me consolidate this, because we have just crossed the most important bridge in the entire subject, and I want to make sure we are both standing on the far side of it. We began by worrying that genuine indefiniteness and hidden definite answer we are ignorant of might be a distinction without a difference. Two stories that always make the same predictions and so can never be told apart. We have now seen that they do not always make the same predictions. In situations involving interference, they make flatly contradictory predictions. The ignorance story forbids cancellation. The genuine superposition story permits and predicts it. Nature shows cancellation. The distinction has teeth. It is not philosophy, it is physics, and it has been checked, and the layered possibilities are doing real work in the world. The amplitude, with its orientation, the quantity that probabilities are squeezed out of, is not a fiction. It is the thing whose cancelling and reinforcing we are directly watching whenever interference appears. This also lets me, finally, show you cleanly where the probabilities come from, in their full and proper form, rather than the rough outline I gave earlier. The quantum state is built out of these amplitudes, one for each possibility, each an arrow with a length and an orientation. As long as the system evolves on its own, these amplitudes evolve smoothly and deterministically, sliding and turning according to that fixed rule I mentioned before, combining and recombining, building up patterns of reinforcement and cancellation. Nothing probabilistic has happened yet. The amplitudes are just doing their deterministic dance. The probability enters at exactly one place, the place where you extract a concrete outcome. To get the probability of any given result, you take the amplitude associated with that result after all the combining and interfering has played out, and you square its length. That is the rule that connects the rich, oriented, interfering world of amplitudes to the humble, between 0 and 1 world of probabilities that we actually observe in our detectors. The orientations, which mattered so much during the combining, get discarded in that final squaring. But they had to be there during the combining because without them there is no interference, and the interference is right there in the data, impossible to remove. So the probabilities are not a sign that the theory gave up. They are the final step of a precise procedure. Lay out the amplitudes, let them evolve and interfere, square the lengths to get the odds. The reason the theory predicts only probabilities for single runs is not that it is missing information about hidden definite values. It is that the most complete possible description, the amplitudes themselves, is genuinely a description of weighted, interfering possibilities, and a single run forces that description to yield one outcome drawn according to those weights. The probability is the faithful echo, in our crude, single outcome world, of an underlying structure that is richer than probability, and that we have caught in the act of interfering. I want to guard against a misunderstanding that often creeps in right about here, because I have been emphasizing how strange and non-classical the amplitude is, and that emphasis can tip over into thinking the whole thing is some loose, mystical, anything-goes affair. It is the opposite of that. The amplitude machinery is rigid, precise, and quantitative. The orientations are not vague vibes, they are exact. The combining of amplitudes follows exact rules. The squaring that produces probabilities is exact. This is why the theory can be so staggeringly accurate, why it produces those 12-digit agreements with experiment we marveled at earlier. The strangeness and the precision are not in tension. The precision comes from the strangeness. It is precisely because the theory tracks these oriented amplitudes and their interference so exactly that it can predict the detailed patterns of bright and dark, of likely and forbidden, with such overwhelming success. A vaguer theory, one that only tracked probabilities and forbade interference, would simply get the patterns wrong. It would predict filled-in regions where nature shows darkness. The amplitude is not a romantic flourish. It is the thing that makes the numbers come out right. There is one more layer of subtlety I owe you before we move on, because it deepens the picture rather than complicating it for its own sake. I have been talking as though superposition is always about a single particle and its possible positions, two routes through an apparatus, that kind of thing. But superposition is far more general than that, and its generality is part of what makes it a structural feature of the framework rather than a quirk of one experiment. Any property the framework can describe, not just position, can come in superposition. A particle's possible energies can be layered together. The possible orientations of a particle's internal magnetic character can be layered together, and, most strikingly, the states of several particles can be layered together jointly in ways that link them so that the possibilities for one are bound up with the possibilities for another, even when the particles are far apart. That joint, linked superposition is its own deep topic with its own profound consequences, and I will not chase it down tonight, because our quarry is narrower and we must stay on its trail. But I mention it so you do not walk away thinking superposition is a special trick that only happens with single particles and openings in a barrier. It is the generic condition of quantum states. Definiteness is the special case. Superposition is the rule. And that reframing is worth pausing on, because it inverts the way we naturally think about the world one more time. We instinctively treat definite properties as the normal default state of things, and we treat any spread or uncertainty as a deviation, a smearing, a departure from the clean default. The framework suggests the reverse. Superposition, the layered coexistence of possibilities with their interfering amplitudes, is the general situation. A state with a single definite value for some property is the unusual, special, sharpened case. The case where all the amplitude has been concentrated into one possibility and the others have dropped to nothing. Definiteness is not the canvas on which possibility is occasionally painted. Possibility is the canvas, and definiteness is what you get in the special corner where the possibilities have collapsed down to one. We live our macroscopic lives entirely in that special corner, surrounded by apparently definite objects with apparently definite properties, and so we mistake the special corner for the whole room. The interference experiments are a way of stepping briefly and carefully out of the corner and seeing the rest of the room, the part where possibilities genuinely coexist and combine. So let me draw the threads of this stretch together and see exactly where it leaves us, because we have come a long way from the cartoon of a particle being in two places at once. Superposition is the layering of genuine possibilities inside a single quantum state. Each possibility carries an amplitude, a quantity with both a size and an orientation, richer than a probability. When a single outcome can be reached by more than one possibility, the amplitudes combine with their orientations before any probability is computed, and they can reinforce or cancel. That cancelling and reinforcing is interference, and it shows up unmistakably in real experiments as patterns of likely and forbidden outcomes. Crucially, interference is something a hidden definite answer cannot produce, because a definite answer means a definite root, and a definite root cannot cancel against the root not taken. The appearance of interference is therefore direct physical evidence that the layered possibilities are real, that in those situations there genuinely is no single definite answer underneath. And the probabilities we ultimately observe come from squaring the lengths of these amplitudes after all their interfering is done, which is why the theory speaks in probabilities for single events while remaining ruthlessly exactly precise about the patterns those events build up. We have, in other words, made good on a large part of the promise. We said there was a real, testable difference between genuine indefiniteness and mere hidden ignorance. And in the phenomenon of interference, we have found it and seen which way nature falls. But notice that we have done this for a particular kind of comparison, the comparison between different routes to an outcome, different possible values of one property at a time. There is a second, subtler face of quantum indefiniteness that interference alone does not fully expose, and it is the one most likely to be confused with ordinary ignorance, because it looks, at first glance, exactly like the kind of limitation a sharper instrument ought to fix. It concerns what happens when you try to pin down two different properties of the same system at the same time, two properties like a particle's location and its motion, and discover that sharpening your knowledge of one does not merely leave the other unknown, but actively destroys its definiteness. That is a different and even more startling form of the same underlying fact, and disentangling it from the ordinary, fixable kind of not knowing is where we have to turn next. There is a moment that everyone hits when they first wrestle with quantum physics, and it is the moment where the whole thing threatens to collapse back into something disappointingly ordinary. It goes like this. You hear that you cannot simultaneously know exactly where a particle is and exactly how it is moving, and you think, well, of course, To find out where something is, I have to interact with it somehow. I have to bounce something off it, shine light on it, poke it. And anything small enough to poke a single particle is going to give it a shove in the process, disturbing its motion. So naturally, the very act of pinning down the location messes up the velocity. That is not mysterious at all. That is just the clumsiness of measurement at tiny scales. Better, gentler instruments, the kind we might invent someday, would do the poking more delicately and recover both numbers at once. The uncertainty is a practical nuisance, not a feature of reality. This reading is so reasonable, so satisfying, that it has its own name in physics law, and it is wrong. Not wrong in the sense of being a silly mistake, but wrong in the sense of mistaking the surface for the depth. It captures something true about the difficulty of measuring, and then it generalizes that truth into a conclusion the actual physics does not support. Untangling exactly where it goes wrong is the work of this stretch of our journey, because hidden inside that untangling is the single, cleanest example of the distinction we have been chasing all along. The distinction between not knowing an answer and there being no definite answer to know. The clumsy instrument story is the ignorance story in disguise, and the real situation, once you see it, is the genuine indefiniteness story wearing its sharpest face. Let me first give the clumsy instrument story its due, because it is not pure fiction. It is genuinely true that measuring a small system tends to disturb it, and that the disturbance can be hard to make small. If you want to locate a particle precisely, you do, in practice, have to use a probe with a short reach. And short reach probes do carry a lot of punch, and that punch does kick the particle's motion around. All of that is real. There is a kind of disturbance-based trade-off that genuinely exists in the act of measuring. The problem is not that this story is false. The problem is that it is not the deep thing. It describes a practical obstacle that sits on top of a far more fundamental fact, and people mistake the practical obstacle for the whole story because it is the part that feels intuitive. The deep fact is not about the disturbance you cause when you measure. It is about what the system can even have to begin with, before anyone measures anything at all. Here is how to see that the deep fact must be something other than measurement disturbance. Cast your mind back to what we established about the quantum state. The state is not an inventory of properties the system definitely possesses. It is the complete description, and it is built out of those layered, interfering amplitudes. Now, a particle's location and a particle's motion are two different properties. And the structure of the quantum state turns out to be such that a state which describes a very sharply defined location is, automatically and unavoidably, a state which describes a very smeared out motion, and the reverse. This is not a statement about what happens when you measure, it is a statement about what the state itself can hold. The sharper the location is built into the state, the more the motion must be spread across many possibilities within that same state, and the more sharply the motion is built in, the more the location must be spread out. The two sharpnesses are tied together inside the description, traded against each other, before any measuring device comes anywhere near the particle. I need to make this vivid because it is abstract and it is the crux. So let me reach again for the idea of a wave, since waves are the one place in ordinary experience where this kind of trade-off shows up plainly and you can almost feel it in your hands. Think about a sound. Suppose I play you a single, pure, sustained musical tone, a clean note held for a long time. That note has a very definite pitch. You could name its frequency precisely. But ask yourself, when does that note happen? It does not happen at a single instant. It is spread out over the whole long duration of the sound. A pure, sharply defined pitch is, by its very nature, smeared out in time. Now consider the opposite. Suppose instead of a sustained tone, I give you a single sharp click, a tiny percussive tick lasting almost no time at all. Now the question of when is beautifully precise. The click happens right then, at that crisp instant. But ask what its pitch is, and the question falls apart. A click does not have a pitch. It is not a note. Squeeze a sound down to a sharp instant in time, and you destroy its definite pitch. Stretch it out to have a definite pitch, and you destroy its sharp location in time. You cannot have both at once, and not because your ears are clumsy. The trade-off is built into what a sound is. A thing that is sharp in time is necessarily spread in pitch, and a thing that is sharp in pitch is necessarily spread in time. That trade-off between sharpness in time and sharpness in pitch is not a special fact about sound. It is a completely general feature of anything with a wave-like character, a mathematical relationship that holds for waves of every kind. And the quantum state, the catalogue of amplitudes we have been building up, has exactly this wave-like character. The property we call location and the property we call motion stand in precisely the same relationship to each other as the timing and the pitch of a sound. They are two faces of the same wave-like description, and the very same mathematics that forbids a sound from being sharp in both time and pitch forbids a quantum state from being sharp in both location and motion. A state with a pinned-down location is like a click spread across all motions. A state with a pinned-down motion is like a sustained, pure tone spread across all locations. The trade-off is not imposed from outside by a clumsy measurement. It is woven into the structure of the state itself, as inevitably as the trade-off in the sound is woven into what sound is. This is the thing the clumsy instrument story misses entirely. The clumsy instrument story says, the particle has a definite location and a definite motion, both sitting there as real definite facts, and our measurement is just too rough to read both off cleanly. But the wave picture says something completely different. It says the particle state simply cannot contain both a sharp location and a sharp motion at the same time, for the same reason a sound cannot contain both a sharp instant and a sharp pitch. There is nothing there for a gentler instrument to recover. You are not failing to read off two definite values because your tools are crude. You are demanding that the state hold two sharpnesses that the structure of the state forbids it to hold simultaneously. No instrument, however perfect, however gentle, however far in the future, can extract a definite value that the state does not contain. The limitation is not in the reading, it is in the thing being read. Let me press on this distinction as hard as I can, because everything that follows turns on it, and it is the single most common place where people quietly slide back into the ignorance picture without noticing. Consider two genuinely different situations. In the first, there is a definite fact that you happen not to know. A coin has been flipped and slapped down under a hand. The coin is definitely heads or definitely tails right now. There is a fact of the matter. You are simply ignorant of it. Lift the hand and you reveal a fact that was already settled. Your uncertainty was about your knowledge, and the world had already made up its mind. In the second situation, there is no settled fact yet at all. The system is in a genuine superposition with respect to the property in question. The amplitudes for the different values layered together and interfering. And there is, as we saw with interference, no single definite value hiding underneath, waiting to be uncovered. Your uncertainty in this second case is not about your knowledge of a settled fact. It is about a fact that is not settled, that does not have a single value to be known. The uncertainty between location and motion is of the second kind, not the first. When a particle's state has a sharp location, and therefore a smeared motion, It is not that the particle secretly has a definite motion that the state is too coarse to record. It is that the motion genuinely does not have a single definite value in that state. In exactly the same robust sense that we proved, through interference, that a particle taking two routes does not have a single definite route. The smear is not a smear over a hidden definite value. The smear is the most complete truth there is about the motion, given that the location has been made sharp. And we are not free to wave this away as mere philosophy, because, just as with interference, it has consequences you can see. The spread in motion is physically real. It expresses itself in how the particle subsequently behaves, in where it ends up, in measurable patterns. A particle whose location has been squeezed into a tiny region will, left to itself, fly apart in its motion across a wide range, and you can watch it do so, precisely because its motion was genuinely spread, not secretly definite. There is a beautiful way to connect this directly back to the interference we just spent so long on, because the two are not separate mysteries. They are the same fact seen from two angles. Recall that interference showed us a particle does not take a single definite route when multiple routes are available and unrecorded. Now think about what a perfectly sharp location would require. A perfectly sharp location is, in effect, a demand that the particle be at one definite point and nowhere else. That all its amplitude be concentrated into a single location, with nothing spread anywhere else. But we have seen that quantum states love to be spread, that superposition is the general condition and sharpness is the special, squeezed case. To force a state into a perfectly sharp location, you have to pile up amplitudes for an enormous range of different motions, all layered together, all interfering, in just the combination that produces a spike at one place and cancellation everywhere else. The sharp location is built entirely out of a vast superposition of motions. That is why it has no definite motion. Its definiteness in one property was purchased by maximal indefiniteness in the other. The two properties are not independent dials you can set separately. They are linked through the wave-like structure of the state, and turning one towards sharpness forces the other towards spread. This linkage between certain pairs of properties is so fundamental that physicists have a word for the pairs that behave this way. They are called complementary. Location and motion are complementary. So are certain other pairs of properties throughout the framework, pairs where sharpening one necessarily smears the other, where the two sharpnesses are traded against each other and can never both be maximized at once. And the word complementary is well chosen, because it captures something important that the cruder talk of disturbance misses. The two properties are not enemies that interfere with our attempts to measure them. They are two complementary aspects of a single underlying reality, each of which gives you a partial view, and neither of which can be brought into full focus without throwing the other out of focus, because the thing itself does not possess both in sharp form simultaneously. You can know a sound's pitch, or you can know its instant, and the choice of which to sharpen is yours. But the thing you are studying does not have both sharp at once for you to know, no matter how you go about it. Now I want to confront, head-on, the most seductive version of the objection, because a careful listener will have one more card to play, and it deserves a real answer rather than a dismissal. The careful objector says, "All right, I grant that the state cannot contain both sharpnesses at once, but maybe the state is not the full story. Maybe underneath the state, beneath the wave-like description you keep insisting is complete, the particle really does have a definite location and a definite motion at every instant, both perfectly sharp, and the wave-like state is just our best summary of a reality we cannot fully access. The trade-off would then be a trade-off in our descriptions, not in the underlying reality. The particle has both definite values. We just cannot build a description that captures both." This is the ignorance picture making its last and most sophisticated stand, retreating beneath the state to a hidden layer of definite values. And it is exactly the kind of move that, on the surface, seems impossible to refute, because by construction, the hidden values are hidden. But this is precisely where the earlier work pays off, and where I can finally close the loop on the promise I made at the very beginning. That the difference between genuine indefiniteness and hidden definite values is not philosophy, but has hard, testable consequences. Because that hidden definite values picture, the one that puts sharp values for everything underneath the state, is not free to predict whatever it likes. If you take seriously the idea that every property has a definite value at all times, sitting there underneath, and you work out carefully what such a picture is allowed to predict for certain cleverly arranged experiments, you find that it is bound by real constraints. Constraints on how the results of measurements on different properties and on systems prepared in different ways can relate to one another. Those constraints take the form of definite limits, ceilings that any hidden definite values picture cannot exceed, no matter how the hidden values are arranged. And the framework of quantum mechanics, with its genuine indefiniteness and its interfering amplitudes, predicts that nature should sail right past those ceilings in specific experiments. The two pictures once again make contradictory predictions. The hidden definite values picture says results must stay below a certain bound. The quantum framework says they will exceed it. I want to make that abstract talk of ceilings concrete, because it is the single most important piece of experimental evidence in this entire story. And left vague, it sounds like a magic trick. So let me give you the shape of how such an experiment actually distinguishes the two pictures, without any equations, just by counting. Imagine you prepare two particles together, in a single shared state, and then send them flying off in opposite directions to two distant laboratories. At each laboratory, an experimenter can choose to measure their particle in one of a few different ways, like choosing which of several questions to put to it, and each measurement comes back with one of two answers. Call them yes or no. The two experimenters are far apart. They make their choices independently, and they make them so close together in time that no signal traveling at any ordinary speed could carry word of one choice over to the other lab before its measurement is done. Whatever each particle does, it cannot be reacting to the choice made at the far lab. That isolation is the whole point of the setup. Now, the experimenters run this many thousands of times, varying their choices, and afterward they bring their two long lists of yes and no answers together and compare them, looking at how often the answers at one lab agree with the answers at the other, broken down by which questions each happened to ask. Here is the crucial part. Suppose the hidden definite values picture is right, and each particle carried with it, from the moment they separated, a definite, preset answer to every question it might be asked. A little sealed instruction list fixed in advance. If that were so, then the pattern of agreements and disagreements across all those runs is forced to obey a certain arithmetic limit. There is only so much coordination that pre-written instruction lists can produce, because each particle's answers were locked in before it left, with no knowledge of what would be asked at the other side. You can work out the maximum possible agreement such preset lists can generate, and it is a hard ceiling. No conspiracy of hidden instructions, however cleverly arranged in advance, can push the correlations past it. Quantum mechanics predicts that the correlations go past it. The particles, described by a single shared state with no definite answers pre-written into either one, come out more coordinated than any set of advance instructions could ever account for. And when the experiment is done, the correlations land exactly where the framework says, above the ceiling, in the region that no preset definite values can reach. That is what it means to say nature exceeds the bound. It is not a figure of speech. It is two stacks of yes and no answers, gathered in separated rooms, that agree with each other more strongly than they possibly could if each particle had been carrying a definite answer all along. And nature, when the experiments are done, exceeds the bound. Carefully, repeatedly, in many laboratories, with steadily tightening rigor that has closed off loophole after loophole, the experiments come down on the side of the quantum framework and against the picture in which every property quietly has a definite value underneath. The hidden layer of sharp values, the last refuge of the ignorance story, is not merely unnecessary. It is, in its most natural forms, ruled out by experiment. There is no consistent way to populate the world with definite values for everything at all times, and still reproduce what is actually measured. The indefiniteness is not a gap in our description that a hidden layer fills in. The attempts to fill it in with hidden definite values make predictions that nature violates. So the indefiniteness stays. It is not ignorance, it is structural. It is in the world. I want to be careful and precise here, because this is a place where it is easy to overclaim, and overclaiming would betray the whole spirit of what we are doing. What the experiments rule out is a particular, very natural class of pictures, the ones that try to give every property a definite local value at all times, independent of what is measured. They do not, by themselves, rule out every conceivable alternative to standard quantum mechanics. There remain a small number of unusual frameworks that try to keep definite values by paying other, strange prices. Prices like allowing distant things to be linked in ways most physicists find harder to swallow than indefiniteness itself. Those frameworks are a genuine part of the landscape, and I am not going to pretend they do not exist. But the simple, comforting, common-sense picture, the one almost everyone reaches for instinctively, the picture where the particle just has a definite location and a definite motion, and we are merely ignorant of them, that picture is not viable. The clumsy instrument story, taken as a claim about reality, is dead. The trade-off is not about our reading of definite values. It is about whether the definite values are there to read. And the answer for complementary properties is that they are not both there at once. So let me draw together what this means, because we have now established something genuinely profound, and I want its full weight to land. The uncertainty at the heart of quantum physics is not a measure of how far our instruments fall short. It is not a fog that better technology will burn away. It is not even, fundamentally, about the disturbance we cause when we measure, though that disturbance is real and sits on top of the deeper fact. The uncertainty is a structural feature of the quantum state, a direct consequence of the wave-like way the state is built, and of the fact that certain pairs of properties are complementary, traded against each other so that the sharpness of one is bought with the spread of the other. When the framework predicts only a range of possible motions for a particle whose location has been sharpened, it is not confessing ignorance. It is reporting, accurately and completely, that the motion does not have a single definite value in that state. And we have not taken this on faith. We have seen, through interference, that layered possibilities are real and not hidden definite answers. And we have seen, through the experiments that exceed those ceilings, that the attempt to restore hidden definite values for everything fails against the data. This reframes the very meaning of the word uncertainty, and I think the reframing is worth dwelling on, because the ordinary word carries baggage that actively misleads. In everyday life, uncertainty is always a relationship between a knower and a fact. There is a fact, and there is my incomplete grip on it, and the uncertainty is the gap between them, a gap that more information would close. Uncertainty, in that ordinary sense, is a property of minds, of knowers, of our limited access to a definite world. The quantum uncertainty we have been examining is not like that at all. It is not a gap between a knower and a settled fact. It is a feature of the system itself, present whether or not any knower exists, present whether or not any measurement is ever made. A particle with a sharp location genuinely has a spread of motions out there in the world, in the absence of all observers. The uncertainty does not live in the gap between us and the particle. It lives in the particle's state. It is, if you like, an objective uncertainty, a built-in indefiniteness that belongs to the physics rather than to our knowledge of the physics. And calling it uncertainty at all is almost an accident of language, a word borrowed from the world of ignorant knowers and pressed into service to name something quite different, something that would be there in a universe with no one in it to be uncertain. There is one more consequence I want to draw out before we move on, because it bridges directly into where we are headed, and it concerns why all of this stays so thoroughly hidden from us in ordinary life. If complementary properties cannot both be sharp at once, and if this trade-off is built into every quantum state, then why does the world around us look so reassuringly definite? Why does a thrown ball seem to have a perfectly good location and a perfectly good motion at every instant, with no trace of this trade-off anywhere in sight? The answer, in outline, is that the trade-off is real for the ball too, but the amount of unavoidable spread it forces is so unimaginably tiny for an object that large that it is utterly swamped, undetectable, lost far below the precision of any measurement you could ever make on a ball. The indefiniteness scales with how quantum the system is, and for anything as enormous and as warm and as constantly jostled as an everyday object, it shrinks to nothing you could ever notice. The trade-off does not switch off. It just becomes so small for large objects that the special, squeezed, definite-looking corner of reality we discussed earlier becomes, for all practical purposes, the only corner we ever see. The ball really does have a tiny, hopelessly unmeasurable indefiniteness in its complementary properties. It is just that for a ball, the indefiniteness is a rounding error beyond all rounding errors, while for a single particle, it is the whole story. And that observation lands us squarely against the last great puzzle, the one we have been circling and deferring since the very beginning. If quantum states are generally these spread-out superpositions, layered with possibilities and complementary indefiniteness, and if that is the complete and correct description of reality at its foundation, then why, when we actually look, do we always see one definite outcome? Why does the spread-out catalogue of possibilities, when it meets a detector, deliver a single crisp answer rather than a smear? Why does the indefiniteness, so robust and so real in the isolated particle, vanish the instant a measurement is made, leaving behind a definite result as plain and unambiguous as anything in the old billiard ball world? We have leaned on the word measurement again and again as the hinge where the spread of possibilities turns into a single outcome, and I have kept promising that the hinge could be understood without invoking minds or magic. It is time to make good on that, to look directly at what happens when a small superposed system makes contact with the vast and warm and complicated world, and to see how definiteness emerges from indefiniteness without anyone needing to be watching at all. We arrive now at the question that has been waiting at the end of every road we have walked. The quantum state is a spread of layered possibilities. We proved, through interference, that the layering is real and not a mask over hidden definite answers. We proved, through the trade-off in complementary properties and the experiments that exceed those forbidden ceilings, that the indefiniteness is structural and not ignorance. And yet, here is the brute, undeniable, everyday fact that seems to make a mockery of all of it. When you actually look, you see one thing. A detector clicks once in one place. A measurement gives one reading, one number, one definite outcome. The smear of possibilities, so robust and so real in the isolated system, somehow always delivers a single crisp answer the moment you check. If reality is genuinely a spread of possibilities, where does the single answer come from? And why, having appeared, does it never look spread out at all? This is called the measurement problem, and I want to be honest with you from the start about its status, because honesty is the whole point of this final stretch. Some of what I'm about to tell you is settled, agreed upon, confirmed physics that every working physicist relies on. And some of it touches genuinely open questions that the smartest people in the field still argue about. The most important thing I can do tonight is to keep those two categories rigorously separate, so that you walk away knowing exactly which parts are bedrock and which parts are live debate. Confusing the two is the source of nearly all the nonsense that gets spoken about this subject, and I would rather you leave with a clear map of what we know and what we do not, than with a comfortable story that blurs the line. Let me start by clearing away the single worst piece of mythology, the one I have been promising to dismantle since the very beginning. You have surely heard some version of it. Reality is created by the act of observation. Nothing is definite until a conscious mind looks at it. The universe is somehow waiting on human awareness to decide what is real, and consciousness reaches into the quantum fog and conjures the world into being by the act of paying attention. This idea is enormously popular. It shows up in films, in self-help books, in casual conversation, and it is not what the framework says. It is not what the evidence supports, and it puts the cart so far before the horse that the horse is in another country. Here is the simplest way to see why it cannot be right. The universe was doing its thing for an unimaginably long stretch before there were any conscious minds anywhere in it. Stars formed and fused and exploded. Atoms assembled into molecules. Whole worlds congealed out of dust. All of that involved quantum systems making contact with other systems and producing definite outcomes, constantly, everywhere, for billions of years, with not a single conscious observer present to do any observing. If definite reality required a mind to look, then nothing definite could have happened until minds existed, and minds could not have come into existence, because the entire physical process of building a mind, every chemical reaction and every interaction, would itself have been waiting for a mind that was not there yet. The view eats its own tail. Whatever produces definite outcomes, it cannot be consciousness, because consciousness arrived absurdly late to a universe that had been producing definite outcomes the entire time. So, if it is not a mind doing the looking, what is it? What is a measurement, physically, stripped of all the mystical decoration? And the answer, the genuinely illuminating answer that has emerged over the past several decades, is that there is nothing special about a measurement at all in the sense of requiring an observer. A measurement is just a particular kind of physical interaction, one where a small quantum system comes into contact with a very large system, a system with an enormous number of pieces, and gets entangled with it in such a way that the small system's possibilities become linked to and recorded in the vast number of pieces of the large one. A detector is not special because it is a detector. It is special because it is big and complicated and connected to its surroundings. And understanding what bigness and complication do to a superposition is the key that unlocks the whole puzzle. But before I can explain what bigness does, I have to make good on a promise I deferred earlier, because the mechanism of measurement runs straight through it. Back when we were dissecting superposition, I mentioned, and then set aside, the strangest kind of layering of all, the kind where the states of two separate systems get woven together so that the possibilities for one are bound up with the possibilities for the other. That weaving together is called entanglement, and it is not a side curiosity. It is the actual physical machinery by which a record gets made, and so it is the actual physical machinery of measurement. We cannot understand why contact with a large system destroys interference until we understand what entanglement does to a possibility. So let me build it carefully. Take our single particle with its two layered possibilities and bring it into contact with just one other system, a second particle, arranged so that the second particle responds differently to the two possibilities. If the first particle is in possibility 1, the second gets nudged into some condition we can call A. If the first is in possibility 2, the second gets nudged into a different condition, B. Now run the framework forward, and something important happens to the description. It is no longer two separate stories. The state becomes a single layered thing, in which possibility 1 for the first particle is fused to condition A of the second, and possibility 2 is fused to condition B. The two fused pairs laid over each other in superposition. The first particle's options and the second particle's conditions are now locked together. You cannot speak of one without the other. That locking together is entanglement, and here is why it matters so much for interference. Recall the rule we worked so hard to establish. Interference, the cancelling and reinforcing of amplitudes, requires that nothing out in the world distinguishes the two possibilities, that there is no fact anywhere about which one happened. But the moment the first particle is entangled with the second particle's condition is exactly such a fact. Condition A versus condition B is a record of which possibility the first particle is in. The information has been copied. And as we saw with the which-way detector, the instant such a record exists, the interference for the first particle alone is gone. Entangling the particle with even one other system begins to wash out its ability to interfere, because its possibilities are no longer cleanly its own. They have been smeared into a second system that now carries the tale of which is which. Now you can see the whole mechanism snap into place, and the role of bigness becomes obvious rather than mysterious. A measurement is not contact with one other particle. It is contact with a detector made of an astronomical number of particles, itself touching the air, the light, the warmth of the room, all of it. So the particle does not get entangled with one partner. It gets entangled, in a cascade, with an immense and ever-growing host of systems, each of which ends up carrying its own copy of the which possibility record. The information branching outward and replicating across more and more of the world with every passing instant. It is entanglement run wild, spreading the record into so many places at once that there is no longer any hope of the possibilities ever finding their way back to each other to interfere. The destruction of interference that we are about to call decoherence is, underneath, simply entanglement with the environment proceeding on a colossal scale. The record is not written in one place. It is copied, redundantly, into a practically uncountable multitude of corners of the surrounding world, all at once. It is worth pausing to connect this spreading record back to the one fact about interference that has done the most work for us all along, because that connection is the whole engine of the explanation. Interference, the visible signature of genuine superposition, appears only when the alternatives remain layered together with no record anywhere of which one happened. We saw that early on with the which-way detector and treated it then as a striking curiosity. Now it becomes the heart of everything. Whether the possibilities stay layered and able to interfere or get separated into a definite recorded outcome turns entirely on whether a record of which way exists out in the world. And the runaway entanglement we have just traced, the particle's possibilities replicating into the detector and from there into the air and the light and the warmth of the room, is nothing other than the making of such a record, on an overwhelming scale. And there is one feature of this spreading that matters more than any other. The feature that makes the whole process so different from anything reversible. In principle, the rules that governed everything up to this point never destroy information. If the record sat in just one tidy place, you could imagine carefully undoing the interaction, gathering the which-way information back up, and restoring the particle's ability to interfere. And, in delicate laboratory setups with very small environments, that is exactly what physicists can sometimes do. But once the record has been scattered into an enormous, warm, jostling environment, that gathering back becomes hopeless in practice. Not because any law forbids it, but because it would mean tracking down and perfectly reversing every last one of the countless pieces that now carry a copy. There is no realistic procedure that could ever do it. The which-way information has not been deleted, but it has been smeared so thoroughly across the world that it is, for all practical purposes, gone beyond recovery. And here is the decisive consequence of that irretrievability, the payoff the whole chain has been building toward. Interference, remember, required something very specific, that there be no record anywhere of which possibility occurred, nothing in the world able to tell the alternatives apart. That condition is now permanently broken. The world is saturated with the record, and so the two possibilities have lost, for good, the one thing they needed in order to combine and cancel. They can no longer interfere with each other. The layering that made interference possible has been destroyed, not by a mind, not by an act of attention, but by the plain physics of information escaping into a vast environment. The possibilities are still present, in a sense, but they have been pulled apart into separate branches that can no longer reach across to one another. This process, the loss of interference once which-way information leaks into a large environment, is what physicists call decoherence. And it is not speculation. It is confirmed physics, observed in the laboratory, its rates measured, the loss of interference watched directly as systems are made to interact more or less strongly with their surroundings. Decoherence is the workhorse that explains the lion's share of the puzzle. It explains why large objects never appear in superposition. A speck of dust, let alone a ball or a cat, is constantly bombarded by air molecules and light, constantly leaking which-way information about its position into its surroundings. So constantly and so thoroughly that any superposition of different positions is destroyed almost instantly, faster than any conceivable measurement could catch it in the act. The dust speck cannot stay in a spread-out superposition of locations because the world will not let it keep the secret. Its position is recorded by its environment 1 trillion times over before you could blink. This is why the definite-looking world of everyday objects looks definite. It is not that the trade-offs and superpositions switch off for big things. It is that big things are so relentlessly entangled with their surroundings that the superpositions decohere into separated, non-interfering branches faster than thought. The special, squeezed, definite-looking corner of reality we keep returning to is the corner that decoherence carves out and maintains for anything large and warm and connected. So decoherence tells us why we never see large objects smeared into superpositions, and why measurements yield results that look definite rather than blurry. The interference, the one thing that would reveal the underlying superposition, has been wiped out by the escape of information into the environment. Whatever you measure something that has already decohered, already been separated into branches that cannot recombine, and so it presents itself to you as definite, as one option rather than a layered many. That is an enormous achievement. It dissolves most of the mystery, and it does so with ordinary physics. No minds required, just large systems doing what large systems unavoidably do. But I promised honesty, and honesty requires me to tell you what decoherence does not do, because this is exactly the place where it is tempting to declare victory and quietly skip past the part that is still genuinely unresolved. Decoherence explains why the possibilities stop interfering. It explains why each branch, taken on its own, looks definite and classical and ordinary. What it does not, by itself, fully explain is why you experience only one of those branches. Decoherence separates the layered possibilities into distinct, non-interfering branches, one for each outcome. But all those branches are still there in the full description. The mathematics, left to run on its own, does not erase the branches you did not see. It keeps all of them. So there remains a question, a deep and genuinely unsettled question, about why you, the observer, find yourself experiencing one specific outcome with the particular odds the amplitudes prescribe, rather than somehow registering the whole branching structure. Decoherence gets you from a smeared, interfering superposition to a set of separated, definite-looking branches. The step from that set of branches to your single experienced result is where the genuine controversy lives. And this is where I have to draw, as sharply as I possibly can, the line between the confirmed physics and the open interpretation, because crossing it without warning is the cardinal sin in explaining this subject. Everything up to this point, the quantum state, superposition, amplitudes, interference, the trade-off in complementary properties, the experiments that exceed the forbidden ceilings, decoherence and the destruction of interference by the environment, all of that is confirmed, agreed upon, not in dispute. Physicists of every philosophical persuasion accept all of it, because all of it is either directly measured or follows from the framework that produces those staggeringly accurate predictions. There is no serious disagreement about any of it. If you remember nothing else, remember that the machinery works and is not controversial. What is controversial? What remains genuinely open after a century of brilliant people thinking hard about it, is the question of what the framework means when it comes to that final step. The step from the branching structure to the single experienced outcome. This is the domain of what are called the interpretations of quantum mechanics, and I want to walk you through the main families of them, not to tell you which is right, because nobody knows which is right, but to show you the shape of the genuine disagreement, so you can see clearly that it is a real and unresolved question, and not a settled matter being dressed up as mysterious. One family of interpretations takes the view that the quantum state and its amplitudes are not a complete description of an individual system at all, but a tool for calculating the probabilities of measurement outcomes, and that asking what is really happening between measurements, beyond what the framework lets you predict, is a question the theory was never meant to answer. On this view, the framework is a supremely accurate instrument for predicting what detectors will do, and the single outcome is simply what you get when you use the instrument. Pressing for a deeper story about why one branch is experienced is, on this reading, pressing past the point where the theory makes commitments. This is, in various forms, close to the attitude many working physicists adopt in practice, sometimes summarized, a little dismissively, as the instruction to stop asking and just compute. It has the virtue of sticking closely to what is testable, and the cost, in the eyes of its critics, of declining to say what the world is actually like. A second family says the quantum state is a real physical thing, the complete description as we have been treating it all along, and that the single outcome comes about because, at some point, the spread of possibilities genuinely collapses to one, a real physical event, in which the other branches actually cease to exist. On this view, there is a genuine, irreducible randomness in the world at the moment a definite outcome is selected. The universe truly rolls dice, and the branch you did not experience is not hiding somewhere, it is simply gone. The challenge for this family is to say precisely when and how this collapse happens, what physical conditions trigger it, and whether the trigger can be made precise without arbitrariness. Some versions propose that collapse is a real physical process that happens spontaneously, more and more readily as systems get larger, in a way that might eventually be tested by experiment, which is part of what makes this family scientifically interesting, rather than merely philosophical. A third family takes the most radical and, to many people, the most disturbing line. It says, take the framework completely literally and refuse to add anything. The state evolves smoothly, the branches separate through decoherence, and nothing ever collapses. Nothing is ever deleted. All the branches are equally real. When a measurement produces several possible outcomes, every outcome happens, each in its own branch, and you, the observer, also split along with everything else, so that there is a version of you in each branch experiencing each outcome. You experience only one, because the version of you asking the question is one branch among many, each equally convinced that its outcome is the single real one. This is the famous many branches view, and people tend to either find it elegant or find it absurd, often passionately. Its appeal is that it adds nothing to the framework, no collapse, no extra rule, just the smooth evolution taken seriously to the end. Its cost is an almost unimaginable proliferation of unobservable parallel realities, which strikes many as too high a price, and others as simply what the equations were telling us all along. There are further families beyond these, including ones that try, as I mentioned earlier, to restore definite values for some quantities by accepting other unusual features, and I will not catalogue them all. The point I want to land is not the details of any one interpretation. The point is the shape of the situation. We have a framework that makes spectacularly accurate predictions, that every physicist agrees about, and on top of which sits a genuine, unresolved disagreement about what the framework is telling us about the nature of reality at the moment of measurement. The predictions are settled, the meaning is not. And crucially, these interpretations are constructed so that, for the most part, they all predict the same experimental results, which is exactly why choosing between them has been so difficult, and why the question has stayed open for so long. They agree on what the detector will do. They disagree on the story behind it. I want to make sure this does not come across as a disappointing shrug, because it is anything but. The fact that the meaning is unsettled, while the predictions are airtight, is itself one of the most remarkable features of this whole subject, and it carries a lesson worth holding on to. It tells you that you can have a theory that works perfectly, that you can rely on completely, that underpins technologies and predicts measurements to 12 decimal places, and still not be sure what it is saying about the deep nature of the world. Knowing how to predict is not the same as knowing what is. That gap between a framework that works and an understanding of what the framework means is a live frontier, and people are doing serious work on it right now, devising ever more delicate experiments to push superposition and decoherence into new regimes, hoping to find some place where the interpretations might finally be forced to part ways and make different predictions. It is not a closed book. It is an open one, with the most interesting chapters perhaps still unwritten. Let me say a little more about why this question has proven so stubbornly hard to settle. Because the difficulty is not laziness, and it is not a lack of cleverness. It is built into the very structure of the problem in a way that is worth understanding, since it tells you something about the kind of question this is. The trouble is precisely the thing I just praised the interpretations for, that they are constructed to agree on every experimental result. Each of these pictures was built by careful people specifically to reproduce the predictions of the framework, the same predictions that win every time in the lab. So if two pictures both reproduce those predictions exactly, then by construction, no measurement you can currently perform will come out differently depending on which picture is true. You can run the experiment 1 billion times, and the collapse story and the many branches story and the just compute story all forecast the identical pile of data. The disagreement is real, but it has been engineered, by necessity, to hide beneath a surface where every experiment looks the same. That is a deeply unusual situation in science, where ordinarily you settle a dispute by finding the experiment that tells the rival ideas apart. So where could a crack possibly open? The most promising frontier, the one that turns this from pure philosophy into something that might one day be decided, lies in pushing the boundary between the small and the large. Remember that decoherence is what hides the underlying superposition for big objects, by entangling them with their surroundings so thoroughly and so fast that interference is wiped out before anyone could ever see it. The interpretations agree completely about what decoherence does, but some of the bolder ideas, particularly the ones that propose a genuine physical collapse, predict that something extra happens as systems grow large, something over and above ordinary decoherence, a real breakdown of superposition that would, in principle, leave a different fingerprint. Other interpretations predict no such extra effect at all, only decoherence all the way up. And that is a genuine difference in prediction, not just in story, if only we could reach the regime where it shows up. This is why some of the most painstaking experimental work in physics today is devoted to taking larger and larger objects, things made of huge numbers of particles, far bigger than single particles, yet still far smaller than anything you could see, and coaxing them into superpositions, then shielding them so fiercely from their environment that decoherence is held off long enough to look for interference. Every time experimenters succeed in showing interference with a bigger object than before, they are pushing the frontier upward, testing whether superposition really does survive into the large-scale world exactly as the framework with nothing added would demand, or whether at some size it begins to fail in a way that ordinary decoherence cannot explain. So far, superposition has survived every step of the climb, with no sign of any extra breakdown. But the climb is nowhere near finished, and the regimes where the boldest predictions differ are still far overhead. The point is that the question is not forever sealed off from experiment. It is hard, perhaps the hardest in the whole subject, but it is the kind of hard that careful work might someday crack open. And that possibility is part of what keeps it from being mere armchair speculation. But step back now from the open question and look at what is not open, because I do not want the genuine controversy at the very end to overshadow the solid ground we have covered, and because the solid ground is enough to deliver the thesis this whole journey was built around. Whatever the right interpretation turns out to be, every one of them shares a common core, and that common core is the answer to the question we started with. The framework, in every interpretation, describes systems with quantum states that encode possible outcomes and their amplitudes. In every interpretation, those possibilities are genuinely layered, not a mask over hidden definite values, as interference forced us to accept. In every interpretation, complementary properties cannot both be sharp at once, as the trade-off and the forbidden ceiling experiments forced us to accept. And in every interpretation, the reason the theory speaks in probabilities is that the most complete description of a system is this catalogue of weighted possibilities, so that a single run can only ever yield one outcome drawn according to the weights. The interpretations argue about what happens to the branches you did not see. They do not argue about whether the underlying description is a description of weighted possibilities. That part is the framework itself, and it is not in dispute. Which brings us, finally, all the way back to the paradox we opened with, the one that looked like a flaw. A theory of unmatched precision that nonetheless refuses to predict single outcomes and offers only the odds. We were tempted, at the start, to read that refusal as a failure, a gap, a sign that the theory was incomplete, and that a better, more complete theory would someday restore the clean, definite answers our intuition demands. I hope it is now clear why that reading is exactly backwards. The probabilities are not a confession of incompleteness. They are a faithful report of the structure of the quantum state, and the quantum state is not an incomplete description waiting to be finished. We tested whether something more complete was hiding underneath, whether there were hidden, definite answers the state was merely summarizing, and we found, through interference and through the experiments that break the forbidden ceilings, that the natural attempts to supply those hidden answers make predictions nature violates. The catalogue of weighted possibilities is not standing in for a definite reality behind it. As far as everything we can test can tell, it is the reality, until an interaction draws a single outcome out of it. And so the uncertainty at the heart of quantum physics turns out not to be an error the theory is apologizing for. It is one of the deepest and most successful structural features of the theory's entire description of reality. It is the thing that makes interference possible, and interference is not a curiosity. It is the basis of an enormous amount of physics and technology. It is the thing that ties complementary properties together, and that tying together is woven directly into the mathematics rather than tacked on as a limitation. It is the thing decoherence acts upon to carve the definite-looking world out of the underlying spread of possibilities. Remove the uncertainty, force the world back into a collection of definite values pinned down at all times, and you do not get a better theory. You get a theory that contradicts experiment, that predicts filled-in bands where nature shows darkness, that cannot exceed ceilings nature sails past. The uncertainty is not the price the theory pays for being incomplete. It is part of what makes the theory correct. I think the most honest and most beautiful way to put it is this. We came into this expecting the world at its foundation to be a vast collection of definite facts, every property of everything pinned to a single value at every instant, with physics as the project of discovering those values and our uncertainty as nothing more than the distance between us and facts already settled. What we found instead is that, at the foundation, reality appears to traffic in the possible rather than the definite. The most complete thing that can be said about a system is often not a list of values it has, but a structured field of values it could yield, weighted by amplitudes that interfere and combine in ways no list of definite facts could reproduce. Definiteness, the crisp, single answer we take to be the bedrock of reality, is not the starting material. It is something that emerges, crystallized out of the field of possibilities when a small system makes contact with the vast and warm and complicated world. The actual is not the foundation. The actual is what precipitates out of the possible. And the uncertainty we kept wanting to explain away, the refusal of the theory to hand us a single answer, was never the theory falling short of a definite reality. It was the theory telling us, with a precision unmatched anywhere in human knowledge, that at the deepest level we have reached, the world is not built out of definite answers at all. It is built out of possibilities, and out of the strange and exact rules by which those possibilities combine, interfere, and, only at the moment of interaction, deliver up the single, definite outcome we mistake for the whole of reality. The uncertainty is not the fog between us and the truth. The uncertainty, as far as everything we can test can tell us, is the truth, woven into the foundation, the most successful and most fundamental feature of the deepest description of reality we have ever managed to write down.